Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. Let's continue the topic controlling degrees of freedom. So, as we discussed earlier, the moment we have one point contact, so if you want to put one constraint, we can always idealize a spherical ball on flat, and this is what we see. So, whenever we have a spherical ball here, and this is the contact we can have, and this is the constraint. So, we can always define one constraint just by putting one contact between the two objects, and in this case the jet translation is not possible. So, that is the constraint, and rest all 5 dots. So, the two translation on the surfaces along the surfaces, which is x and y, and all the rotations along x, y and the z direction, they are all possible. So, yes, so just by putting one contact, defining one contact between the objects, we can impose one constraint and remove 1 degree of freedom. So, similarly, if you want to have two constraints, so we can always define two contacts. So, like for instance, in this case link on flat, we define two contacts and then we can have two constraints. Similarly, we also talked about the ball on V groove. Here also we have two contacts and we get two constraints that we already discussed in the last lecture, but here we can clearly see here in this case the two constraints are the z and y translation in this case. So, which is perpendicular to the V groove. So, it cannot move along y and z axis, but again you have all the rotations and one translation, which is the x axis here in this case, which is aligned to the V groove axis. Similarly, if we want to have three constraints, of course, we can just go on increasing the number of contacts, and we can define what kind of constraints we can get, what kind of devices or the mechanical connections we can get. The easiest way is to get three contacts on the surfaces which is three link balls suitably distributed on a flat. And in this case, what we observe that there will be a planar motion only. So, it can move in the plane. So, x translation and y translation and z rotation we will have. And what constraints we have is the z translation, which is not possible, and the two rotation along x and y axis, which is constraint. Similarly, we can also define ball in trihedral hole. So, where three surfaces we define by using a tetrahedron structure. So, tetrahedron hole. So, some manifestation of similar design we can use, but again here we have three contacts on the surfaces and we get again 3 constraints here, and here it will be more like a ball and then coming from the 3 sides, and it constrains the position along x, y, z, and that is why whenever we want to locate the position of any object, we can use this approach. Similarly, what we can also do is we can use one V and one flat. So, link with one ball in groove and other on flat, and here also we can see what is the degree of freedom and what are the constraints. So, this we have been already discussed. What about if you keep on increasing the number of contacts and or if you want to have connections with more constraints. So, for instance, if you want to have 4 constraints. So, we can have 4 balls suitably distributed on 2 inclined flats. I think this is something maybe we have to check why or what are the other options, whether we can have 4 ball contact on a flat surface, if not why. So, yeah, so moment we start defining more contacts, sometimes it is difficult to visualize, and that is why it is important to understand how to place them. So, for 4 constraints, yes, we can use the earlier cases. So, for instance, if we put one ball in a tetrahedral hole, 3 constraints we can provide and the other we can put on a flat. So, again we get a 4 constraint, 4 contacts. So, we will get 4 constraints. Of course, I think it can be homework also, home assignments, where you can try these things at home. You can make some 3D model or CAD model and try to visualize, and you can actually animate by just defining these contacts and making this kind of tetrahedral hole or flat or V groove, and then you can see yourself what are the degrees of freedom and what are the constraints. It is also possible to achieve 4 constraints by having 2 balls in a V groove. So, again with a 1 ball and 1 V, that gives us 2 contacts. So, again 2 times 2, 4 contacts. We can also have 3 balls with 2 on a flat and 1 in a groove. So, yeah, different cases we can think of, and then we can also practice and try to visualize. Good thing is, if we try to animate using this kind of assembly mating, what we realize that if it is exact constraint design and if we change any of the parameters, so any deviations if you have in the parts, actually it just shifts and move to different locations, but the assembly is still valid. If we compare these kind of things with the conventional assembly processes, what we realize that even if we go change the dimensions or tolerances to 0.001 millimeter, or kind of if it's the we are talking about the perpendicularity of the surfaces, even if means just to fool the software we can put a very small number, negligible, even then it will not work, because the way it is defined is not exactly constrained, and moment something changes, they will not align, they will not conform, and since it is over constrained design, the assembly will fail. So, it will start showing red flags. So, I think that is also one way to see. So, we will see some examples here, and like first case, yeah, here what we see here is we have two V group defined, and the V groups are parallel, and then we have this object. So, what we have defined is this constant. So, V a ball on a V give two constraints. So, 2 plus 2 4 constraints we have. So, ideally we should have removed 4 constraints, and there should be 2 degrees of freedom. So, in this case what will happen, it can slide along the V groups, and it can also rotate along the axis. So, these are the dots. These two are the degrees of freedom. One can ask, what if the V groups are not parallel? So, I think this is the question one should ask, and you should start doubting yourself, and just try develop this CAD model in any of the packages. Instead of making parallel, just try to put them differently, maybe 1 degree deviation. If you put, what happens? There will be still some, you can still move along the surface, along the axis, one of the axis, and you can also rotate. Yes, since they are not parallel, you will see some parasitic motion, which will be dependent on the one of these degrees of freedom. So, this you can visualize. At the same time, if we put the same object with the two ball ends on a single V group, so again we have this constraint defined. So, two contacts and two constant at the ball ends, but we realize that yes, it can move along the V groove axis, and at the same time it can also rotate. So, very easy to visualize. What happens when these V groups are not parallel, whether if they are perpendicular or even if like they are not even intersecting, but different planes and they are in the oblique directions, what will happen? How to define that? And again what you see, there is always 4 constraint, 4 contact defined here. So, you will have the rotation, and since the V axis is now perpendicular to each other in this case, and they are free to slide, but they are constrained by the length. So, we will find a remote center of motion, and along that axis it will rotate. So, instantaneously this will rotate, but yes, this axis will move. Similarly, we can have similar thing in this case. So, it can slide along this V axis and this V axis. Again, it is constrained by the length. So, we will have one rotation along its own axis, but there will be another axis defined and along which it will rotate. So, for instance, if I have this 3D printed part. So, this is I have with the 2 V group defined here. So, you can see, so 1 and 1 here, and if I have this dog bone kind of structure or dumbbell kind of structure 3D printed. So, what we can see is, yes, I can slide along one of the V group if I make the contact. So, there are 2 contacts defined, you can see clearly. So, 2 contacts I can move, and I should be able to define all the 4 dots in this case. Moment it comes in contact with the flat. So, it is a 2 plus 1 3 contacts. So, 3 constants I should be able to see, and 3 degrees of freedom I should be able to explain. Similarly, moment it falls to the another V group. So, I have like 2 V groups, like one this and the other here, and if I just press them so that they are always in contact. So, 4 contacts. So, 4 degrees of freedom, 4 constraints. So, I have 2 degrees of freedom, and what you can see, it can rotate along its own axis, but at the same time it can slide along. The ball will slide on the V groove, and since it's a constrained by the length, so we will get this kind of motions. So, very easy to visualize here. So, again you can see here. So, if we proceed similarly, and what if we have, or somehow we manage to get 5 contacts. So, 5 constraints can be defined. So, then we have to find those 5 contacts and how to define them. I think it may not be very easy to visualize that, and many times what you also realize what is saying, the last one, 5 balls suitably distributed on 2 inclined flats. So, again is some exercise for you, and maybe you have to also understand why you need 2 flats and inclined flat. So, there should be some angle between the 2 surfaces, they should be inclined, and how you can distribute 3 plus 2, or whether 4 plus 1 is possible, that is the exercise. 2 plus 2, 2 plus 3 is possible. So, different combination you can think of. Again 4 ball with 1 V group and 3 on a flat. So, 3 plus 2, 5 again. You can have 3 ball with 2 in V groups. So, 3 and 2 in V groups means 4 and plus 1 on a flat. So, again 5, or you can have just 2 ball, one in a trihedral hole and the other in a V groove. So, in all these cases you see there are 5 contacts made differently, and we should be able to find 5 constraints. If we are not able to do that, it means there is something wrong in the configuration, the geometry does not allow that, and that is why I think it is important to understand the physics or the mass of it, which kind of geometry can be fitted with what kind of contacts. So, for instance, what we stated in the beginning and what we usually say most of the time, that for a flat surface you just need 3 contacts. So, you cannot have more than 3 contacts on a flat surface. If it is there is a over constraint, or there is some elastic deformation in the object we are accounting for. So, 2. So, anything less than 3, 3 and less than 3 is possible on a flat surfaces, but we can have other kind of surfaces like cylindrical surfaces or spherical surfaces. So, we can think of, and then we try to see like what kind of geometry will be permissible, what kind of geometry we can use in combination with different kind of ball contact. So, very good example here. So, we can have 3 contact here. So, 1 surface and 2 contact here, a line. So, 3 plus 2 again 5 contact. So, 3 contact, and so we can always idealize with respect to the constraint directions, and one should be able to see that there will be only 1 degree of freedom, which is the translation as shown. So, which is this axis. So, this is the only degree of freedom, and if we look at it closely, what we realize that if the 3 balls are in contact to the top surface, it defines one planar surface. So, planar constraints we provide. What is needed now is to block this motion. So, this x motion. So, it has to be blocked. So, we need to provide the constraints along that direction, and if there are 2 parallel constraints in that direction, they will also eliminate the rotation along the z axis, and That is how we constrain all the rotations, all the 3 rotations, and true translation along x and z axis that can be constrained, and what is only allowed is this translation, which is the y axis in this case. So, a very good example. Again, what one can do is we can just use any CAD packages, can design a block and another L kind of shape with this 5 ball contact define, 5 ball ends if we define, and if we try to assemble them in the CAD packages. So, like for instance, in SolidWorks we call it mating, and when we define through only the, so what we have to define is the surface and the ball contact. So that it's a only point contact, and when we define these 5 contacts, what we realize that we can just move along this axis what is defined here. One good thing to check is, even if there is no perpendicularity maintained, any tolerances, any deviations, if you want to make, it will still work. And this works because it is exactly constrained system, and same thing will happen in reality also, because we can have objects with some deviations, we cannot have the exact numbers, but if it is exactly defined, the assembly will not fail, it will still work. Yes, because of those small deviations, we will have errors, but they are defined well along the length, and we can later compensate using our controller or any other systems. So, next is what happens if we define 6 constraints. So, we remove all degrees of freedom and then we get a new term, and what is called is kinematic clamp. So, when we provide constraint in all 6 degree of freedom between the 2 objects, it ceases to move. So, we removed all degrees of freedom. So, there will be no relative motion between the 2 objects, and therefore, it can be considered clamped. Clamped because yes, position is defined and they are going to the same location all the time, and okay, we have to use some other methods to bolt it or fix it or to lock it, but the position is locked and we can use these terms. And many times in the literature we see this term kinematic clamps, and wherever we are saying kinematic clamps, it means there is no relative motion, and if it is an ideal kinematic clamp, there will be 6 independent contact points. So, these are some examples I have already mentioned earlier. So, like trihedral hole, V groove and flat, or 3 V's, and on another or on the top platform we can have 3 ball ends, and usually they are called type 1 and type 2 Kelvin clamps. So, just remember, if it is 3 intersecting V grooves, it is a type 2 Kelvin clamp, and type 1 is tetrahedral, trihedral hole, V groove and flat. So, again 3 constraint defined by this trihedral hole and the ball end, one a spherical ball end, 2 more defined here, V and the sphere 2, and the 6th one is defined by this one on the flat surfaces. So, again 6, and we establish the kinematic connection, and it's exactly constrained, and we have to keep reminding ourselves that if it's exactly constrained, then it will always return to the same location and position. So, it's a well defined, and the repeatability will be very good, and no precision dimensions required. So, the tolerances can be relaxed, and that means the cost can be lowered. So, even with the imprecise precision parts, we can still achieve very good repeatability, precision assembly, provided we use exact constraint design approach. So, for instance, again for more illustration, we have the trihedral hole here. So, 3 constraint defined here, 3 constraint when they make contact. Similarly, if the V groove, it make two contacts here. So, here this is the B groove coming in contact, and the third one is simply the flat. So, I will say this flat surface coming in contact with this one other contact. So, 3 plus 2 plus 1. So, total 6 constraints. So, this is the surface I am talking about. So, it comes in contact, and then I will have total 6 constraints. So, exactly defined, and that is what we are referring to Kelvin clamps. And here again I also 3D printed and try to see myself, and we can try to visualize what happens when we start increasing the number of contacts. So, for instance, we can start backwards also, we can start with the flat. So, one flat, and then how the different motions can happen. If we have the V groove, then what kind of motions we can have. And when this ball comes in contact with the V groove, so 3 contacts. So, what we realize, moment we do this, we lock the position. Although the top plate can rotate, right, along different axes, but that particular ball is getting located by the trihedral hole, because it has 3 contacts. So, it is defining 3 constraints. So, no translations. So, if you I just want to move along x, y, z, I cannot. Yes, I can rotate, because that is the degree of freedom. Moment I establish the V and the ball. So, now I have 5 contacts made. So, 3 plus 2. So, what you can see is it can only rotate. So, I can define one axis and it can rotate, and moment it comes in contact with the 6 with the flat surface, yes, all 6 now defined. So, if I apply enough nesting force and suppose I press it and try to move it, I cannot, because it is well defined now, exactly constrained, all 6 providing enough constraints, and I will not have any motion. So, even this 3D printed part works well, and I can do it blindly. Every time I take it and put them back, it will go to the same location. Yes, if there is any offset, it will be there, but that can be measured and can be adjusted. So, I can have some adjustment mechanism inbuilt, and I can later adjust it. So, that you can see that I do not have to use any particular tool or any jigs and fixtures for this. This is inbuilt, is built here, and I do not have to rely on other methods. So, many times suppose I have to in normal design, we just rely on the bolts. So, we try to somehow bring them together and align it and then fix it, and moment we tighten it, they will go off. But if we have these fixtures embedded, and if we use the exact constraint design principles, actually they will go to the same location, and later I can design some clamping mechanisms. or even the bolts I can use later. So, bolt is only for fixation. The location is defined by these features. What we also try to see here, observe that the location is defined by the trihedral hole, so that point does not move. But if there is any thermal expansion, the other ball can move along the V groove, and the third ball on the flat can also slide on the flat surface. So, actually if there is a large temperature change, and if there is a differential variation, different alpha thermal expansion for the objects, it still works because it's not over constraint, is exactly constrained, and if there is any thermal expansion with respect to each other, since not over constrained and the local displacement is allowed, so that will accommodate. So, any change in the length between the 3 ball or even the contact points here, it will be accommodated automatically. Yes, in this case it is not symmetric, so it will go off. So, we will also talk about concept of thermal center, and that is used in precision machine design. Similarly, if we go for this design, so for instance, the 3 V's here and the spherical ball. So, here we all have 2 contacts, and all these V's are radially defined. So, yeah, it is very clear from here. So, and moment they come in contact, they will again. So, how to know that they are exactly constrained and there is no over constraints, because there are only 6 contacts, and if it is not exactly constrained, there will be some degree of freedom there, still there, but in this case it will not be. And yes, there are various methods to know that. So, mathematics we can talk about later, or yes, I can refer to some other materials. If time permits, we can also discuss about those methods, but in general we can see that many times we can visualize, and not very difficult to find it if it's a regular object. Of course, if it's a irregular geometry, then it's a difficult, and maybe we have to find some ways, some method to know how, if there is any over constraint here. So, again I 3D printed here, and what we see here is 3 radial V grooves here. So, they are all intersecting, but all the V grooves on the same surface here, and the other part we have the 3 ball ends here. Again here, when we start, we can also start with the 1 V groove. So, what we see here is 1 V and the ball, they can always move along that V groove. So, if there is any relative change, it will allow that expansion and contraction. We can again see one by one 2 contacts, and if we make 2 contacts, right. So, it can rotate actually, because these 2 is very similar to 2 V and the 2 ball. So, that motion we will have. Moment the third one contacts with another V, it will go to the same location. So, I can do it blindly. I do not have to even look at the part, and what I will see is it's always defined, and if these V's are well defined, it will always go to the same location. So, I do not have to even align it. So, if it's cylindrical surfaces, and if you want to align the 2 axes to 2 shafts or to any cylindrical objects, and if you make this kind of features, they will always go to the same locations, and later I can use the bolts or the clamps to lock their position. what we will also realize that if there is any thermal change, any variation, each pair can deviate, so expand and contract. And what we realize that the center of this will invariant, the position will not change if there is any thermal change in it. It will just radially expand and contract, and the individual ball can slide on the grooves, so it does not provide any kind of thermal stresses also. So, there will be no stress buildup because of the thermal expansion or contraction. So, again very good example, and that is why it is used very often by optomechanical people or by physicists in the old time. So, that is why it is called Kelvin clamp. So, in optics, in optical systems it is very frequently used, but since what I have discussed in the beginning, that something which was very precise in the past, maybe 60s or 80s, is a normal in today's time. And suppose if you want to go further, then of course we have to still use those concepts and then build the setup of the system from there. So, we cannot deviate from the basic principles, how to achieve precision, how to achieve good repeatability. So, we have to ensure that they are exactly constrained, and then we can start addressing the limitations, what kind of problems we can have, and whether we can address them, whether we have the solution for that. If not, then how to circumvent, how to alleviate those problems. So, this is one great example again. What happens if not regular geometry, but different kind of. So, here suppose if it is very thin. So, although thickness we see, but if it is just a thin tube kind of structure, and we define V groups here, 3 V groups, and we just try to locate this object with respect to this tube and want to locate it centrally. What is the approach? Whether we can use this systematic approach of exact constraint design and can get the same results. So, again if we assume that is a thin tube, so there will be 2 contact defined here, 2 contact defined here, and 2 contact defined here. So, it is a very similar to what we just discussed. So, 3 ball in a tetrahedron in 3 V groups, and if we have this, then why it should not work? So, we can also see from the example. So, again I have 3D printed. So, I have thin tube with the notches, V notches, and now I have this structure with the 3 spiders here, 3 bars. What if I place it like this? And what do you realize? Moment I place it and press it, it's going to the same location. So, it's centrally located. I don't have to do anything. So, moment I have that feature, it's not going to move anywhere. So, it's very important to understand that if we are following this principle, if we are putting the constraints the way it's required, it cannot go wrong. So, even a thin tube with this kind of contact, so we can have bar or cylindrical surfaces, and if we just make them touch, if we establish the contact, it will go to the center every time. I can do that. So, again it is a exactly constrained system, 6 constrained and defined. So, it will go to the same location. I do not have to use any kind of radial features here, which is the normal practice. So, normally if we have to locate something centrally and want to align the axis, we always go for some radial adjustment, but what you see here is not required. The 3 simple notches can do that. So, suppose if you are designing something, some big vessels or some cylindrical things, and on top of it you have to put a plate which should be symmetrical to that or should be aligned to the hole or to the circumference. What we need to have is just these 3 notches and this feature, we just align them, it will go to the same location, and then later we can clamp it, lock it, bolt it. So, it can be as simple as this, no tooling required, and this will work. Similarly, what happens if we have a cylindrical bar here and try to locate it. So, again we have 2 V's here. So, again 2 V's here. So, 4 constraints. So, what we see here, again I have printed it. So, I have 1, 2 V's, and if I put it there, what I see, it can translate along the surface and can rotate, which we can see here also. So, it can translate and rotate. But we want to fix it. So, how to fix it? So, suppose what if I just make another V here. So, some projection I made and then I made another V. So, I defined another V contact. So, again it is a very thin structure and 2 V's to support the bar and another V just to lock the position. So, what we do, if we just go there and now all the 6 contacts made is now locked, the position is locked, it cannot move, with respect to the bottom structure and cannot rotate. So, again this is something we have to learn in this course, that if it is exact constraint design, we do not have to do any kind of unnecessary jugaad, what we refer to many times, and we can do it very scientifically, very accurately using these methods. So, what we see, yes, we have this feature, we can locate it. In many cases, what we do, we locate and then we locate using these kind of screws. What happens? If it's locked, it's okay, but with the usage, there might be wear and tear, and then the clearances at the hole, they will also have some clearances here. So, there is a hole and there is a threaded here. So, it can go on the thread, but the clearances here will give some problem and it is not very good design compared to this one. So, of course, this will be preferred. So, I think knowing kinematic design principles or exact constraint design, I think we can design the contacts, can design the mating, how the parts should be assembled, how they should communicate with each other, and that is what many times I refer, that the components, the parts, they also talk, and talking is the constraint. What kind of constraints we want to have, what is the degree of freedom we want to have, and if we listen to that and based on that if we define the constraints, then definitely we will not have a problem and we can get a very repeatable performance, and that way the predictability, the repeatability, the precision, and later we can achieve very accurate systems. So, for high level of predictable behavior, we want to know what happens if something changes, and if we really want to predict that, and we want to have minimum number of accurate dimensions. We do not want to increase that number. If the dimensions and the tolerances are very high, then it leads to a lot of cost, and many times but we also realize that there is limitations because of the processes, the manufacturing processes, because of the fabrication techniques used. So there are limitations, and sometimes we cannot get those tolerances. So how to minimize that requirement, the minimum number of accurate dimension, and if you want to have that, so these two, predictable behavior, minimum number of accurate dimensions, exact constraint design is necessary condition. Cannot have if it's not exact constraint design. If there is over constraint, we have to find some midway. So definitely if you want to have a system with a predictable behavior with a very good deterministic properties, we need to go for exact constraint design. One very good example of any over constraint design and why we pay a lot of price, we can just go through this example and we'll understand. So any 4-column press, if we try to see, so there are 4 guides here, and then so there are 4 of them. Similarly here also, if you see 1, 2, 3 and 4, what is the requirement here? Requirement is only this, we just want to move along this axis, we move that part. So what is the over constraint here? How to find it? So if you just look at this, so probably if we just talk about this center line, and suppose if this is the thing, usually what we will have is 2 bushings here. So 1 bushing here and 1 bushing here. So if we just talk about 1 bushing and one guide or shaft here, so it's a cylindrical pair, so it can slide and it can rotate. So 2 DOF it will have. So 1 bushing gives 2 DOF and providing 4 constraints. Each bushing will provide 4 constraints. So if you look at this system and if this is the arrangement, there are total 8 bushings, 4 on top and 4 at the bottom. 1, 2, 3, 4, 5, 6, 7, 8. And we are holding it. So it's a parallel configuration. So we are trying to hold, so each bushing and the guide, 4 constraints, 8 times. So total 32 constraints we have already imposed in this system. There are total 32 constraints. What is ideally required? This upper plate should move only in this direction. So only 1 DOF. The requirement is only 1 DOF. For any rigid body, total 6 minus 1. So there are only 5 constraints required. This is the requirement. Only 5 constraints. What we are providing is 32 constraints. So how many are redundant? Number of over constraints. 32 we are providing, 5 are only required. So, 27 times is over constraints. 27 times a simple price, and that is the reason we pay very huge price, or the cost is so high if we go for higher precision, because then the tolerance has to be defined, the assembly, the parallelity, the straightness, the location of each and every hole, we are defining the bushings. So, now you can imagine how many ways it can go wrong, and we can't even allow one, because if there is a deviation it will get us stuck, or the holes has to be bigger. So, there will be a lot of clearances. So, suppose if you are going towards a micron kind of application, we cannot achieve that, or we cannot have a very large range of motions. What is required is only 5 C's, 5 constraints. So, a lot to deliberate on, a lot to think about it, and what should be the better way to design these kind of systems. Yes, there are some ways, and this example from Professor Sumer's book, Design of Precision Machines. And again here talking about only 5 contacts, 3. So, on top we have 3 contacts and bottom we have 2. So, 3 plus 2, 5 constraints. And if we look at it closely, what we realize that we eliminate 5 dots except this motion. So, this motion is not constrained, but all other 5 dots, 2 translations and the 3 rotation, they are constrained using these 5, some in pair, and the way they are placed, they are inclined, and is basically what if there is any change in the temperature, and if there is any thermal variation, the expansion and contraction, how it can be allowed, and it should not get stuck. Of course, this is without preload. If with preload we can use symmetric design, and we can have all 8 bushings or 8 contacts. 3 of them will provide the preloading. So, that is why you see the springs here. So, loaded preloaded with the springs. So, there is a compliance in between, and you rely on the stiffness of those springs there. So, it's possible, but yes, to really get this thing implemented in a real system, I think one has to deliberate and do a lot of designing, and we have to address issues one by one. So, what we did here in this case is we just tried to define those 5 contacts. So, we developed one model in one of the CAD packages, and what we see here is with the 5 we can just animate it, and you do not depend on the tolerances of individual parts. So, what is the angle of the V grooves, how flat is flat, what is the location of those. So, if it is a slightly off, it does not matter. So, it provides 5 constraints and 1 degree of freedom, which is this one. So, we will stop here, and we will continue. We will take some more examples. We will try to see different elements to provide constraints. We talk about some kind of lectures. So, we will take some more examples. We will talk about different kind of designs, and we try to learn. Thank you.